Chapter 4 of How It Flies, or Conquest of the Air. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Tom Penn. How It Flies, or Conquest of the Air, by Richard Ferris. Chapter 4 Flying Machines. The term flying machines is applied to all forms of aircraft which are heavier than air, and which lift and sustain themselves in the air by mechanical means. In this respect they are distinguished from balloons, which are lifted and sustained in the air by the lighter than air gas which they contain. From the earliest times the desire to fly in the air has been one of the strong ambitions of the human race. Even the prehistoric mythology of the ancient Greeks reflected the idea in the story of Icarus, who flew so near the sun that the heat melted the wax which fastened his wings to his body, and he fell into the sea. Perhaps the first historical record in the line of mechanical flight worthy of attention exists in the remarkable sketches and plans for a flying mechanism left by Leonardo da Vinci at his death in 1519. He had followed the model of the flying bird as closely as possible, although when the wings were outspread they had an outline more like those of the bat. While extremely ingenious in the arrangement of the levers, the power necessary to move them fast enough to lift the weight of a man was far beyond the muscular strength of any human being. It was a century later, in 1617, that Veranzio, a Venetian, proved his faith in his inventive ability by leaping from a tower in Venice with a crude parachute-like contrivance. He alighted without injury. In 1684 an Englishman, John Wilkins, then Bishop of Chester, built a machine for flying in which he installed a steam engine. No record exists of its performance. In 1678 a French locksmith by the name of Besnier devised what seems now a very crude apparatus for making descending flights, or glides, from elevated points. It was, however, at that date considered important enough to be described in the Journal of the Savants. It was a wholly unscientific combination of the dog paddle motion in swimming, with wing areas which collapsed on the upward motion and spread out on the downward thrust. If it was ever put to a test it must have failed completely. In 1742 the Marquis de Barqueville constructed an apparatus which some considered to have been based on Besnier's idea, which seems rather doubtful. He fastened the surfaces of his airplane directly to his arms and legs, and succeeded in making a long glide from the window of his mansion across the garden of the Tuileries, alighting upon a washerwoman's bench in the Seine without injury. Paucton, the mathematician, is credited with the suggestion of a flying machine with two screw propellers, which he called pterophores, a horizontal one to raise the machine into the air, and an upright one to propel it. These were to be driven by hand. With such hopelessly inadequate power it is not surprising that nothing came of it, yet the plan was a foreshadowing of the machine which has in these days achieved success. The Abbé Desforges gained a place in the annals of aeronautics by inventing a flying machine of which only the name orthopter remains. About 1780 Carl Friedrich Meerwein, an architect and the inspector of public buildings for Baden, Germany, made many scientific calculations and experiments on the size of wing surface needed to support a man in the air. He used the wild duck as a standard, and figured that a surface of 126 square feet would sustain a man in the air. This agrees with the later calculations of such experimenters as Lilienthal and Langley. Other of Meerwein's conclusions are decidedly ludicrous. He held that the build of a man favors a horizontal position in flying, as his nostrils open in a direction which would be away from the wind, and so respiration would not be interfered with. Some of his reasoning is unaccountably astray, as for instance his argument that because the man hangs in the wings, the weight of the latter need not be considered. It is almost needless to say that his practical trials were a total failure. The next prominent step forward toward mechanical flight was made by the Australian watchmaker Dagan, who balanced his wing surfaces with a small gas balloon. His first efforts to fly not being successful, he abandoned his invention and took to ballooning. Stenzel, an engineer in Hamburg, came next with a machine in the form of a gigantic butterfly. from tip to tip of its wings it measured 20 feet, and their depth fore and aft was 5½ feet. The ribs of the wings were of steel and the web of silk, and they were slightly concave on the lower side. The rudder tail was of 2 intersecting planes, one vertical and the other horizontal. It was operated by a carbonic acid motor, and made 84 flaps of the wings per minute. The rush of air it produced was so great that anyone standing near it would be almost swept off his feet. It did not reach a stage beyond the model, for it was able to lift only 75 pounds. In 1843, the English inventor Henson built what is admitted to be the first airplane driven by motive power. It was 100 feet in breadth, spread, and 30 feet long, and covered with silk. The front edge was turned slightly upward. It had a rudder shaped like the tail of a bird. It was driven by 2 propellers run by a 20 horsepower engine. Henson succeeded only in flying on a downgrade, doubtless because of the upward bend of the front of his plane. Later investigations have proven that the upper surface of the airplane must be convex to gain the lifting effect. This is one of the paradoxes of flying planes which no one has been able to explain. In 1845, von Dreiberg, in Germany, revived the 16th century ideas of flying with the quite original argument that, since the legs of man were better developed muscularly than his arms, flying should be done with the legs. He built a machine on this plan, but no successful flights were recorded. In 1868, an experimenter by the name of Winheim added to the increasing sum of aeronautical knowledge by discovering that the lifting power of a large supporting surface may be as well secured by a number of small surfaces placed one above another. Following up these experiments, he built a flying machine with a series of 6 supporting planes made of linen fabric. As he depended upon muscular effort to work his propellers, he did not succeed in flying, but he gained information which has been valuable to later inventors. The history of flying machines cannot be written without deferential mention of Horatio Phillips of England. The machine that he made in 1862 resembled a large Venetian blind, 9 feet high and over 21 feet long. It was mounted on a carriage which traveled on a circular track 600 feet long, and it was driven by a small steam engine turning a propeller. It lifted unusually heavy loads, although not large enough to carry a man. It seems to open the way for experiments with an entirely new arrangement of sustaining surfaces, one that has never since been investigated. Phillips' records cover a series of most valuable experiments. Perhaps his most important work was in the determination of the most advantageous form for the surfaces of airplanes, and his researches into the correct proportion of motive power to the area of such surfaces. Much of his results have not yet been put to practical use by designers of flying machines. The year 1888 was marked by the construction by Sir Hiram Maxim of his great airplane which weighed 3 1/2 tons, and is said to have cost over $100,000. The area of the planes was 3,875 square feet, and it was propelled by a steam engine in which the fuel used was vaporized naphtha in a burner having 7,500 jets, under a boiler of small copper water tubes. With a steam pressure of 320 pounds per square inch, the 2 compound engines each developed 180 horsepower, and each turned a 2-bladed propeller 17½ feet in diameter. The machine was used only in making tests, being prevented from rising in the air by a restraining track. The thrust developed on trial was 2,164 pounds, and the lifting power was shown to have been in excess of 10,000 pounds. The restraining track was torn to pieces and the machine injured by the fragments. The dynamometer record proved that a dead weight of 4½ tons, in addition to the weight of the machine and the crew of 4 men, could have been lifted. The stability, speed, and steering control were not tested. Sir Hiram Maxim made unnumbered experiments with models, gaining information which has been invaluable in the development of the airplane. The experiments of Otto Lilienthal in gliding with a winged structure were being conducted at this period. He held that success in flying must be founded upon proficiency in the art of balancing the apparatus in the air. He made innumerable glides from heights which he continually increased until he was traveling distances of nearly 1/4 of a mile from an elevation of 100 feet. He had reached the point where he was ready to install motive power to drive his glider when he met with a fatal accident. Besides the inspiration of his daring personal experiments in the air, he left a most valuable series of records and calculations, which have been of the greatest aid to other inventors in the line of artificial flight. In 1896, Professor Langley, director of the Smithsonian Institute at Washington, made a test of a model flying machine which was the result of years of experimenting. It had a span of 15 feet and a length of 8½ feet without the extended rudder. There were 4 sails, or planes, 2 on each side, 30 inches in width, fore and aft measurement. 2 propellers revolving in opposite directions were driven by a steam engine. The diameter of the propellers was 3 feet, and the steam pressure 150 pounds per square inch. The weight of the machine was 28 pounds. It is said to have made a distance of 1 mile in 1 minute 45 seconds. As Professor Langley's experiments were conducted in strict secrecy, no authoritative figures are in existence. Later a larger machine was built, which was intended to carry a man. It had a spread of 46 feet and was 35 feet in length. It was 4 years in building and cost about $50,000. In the first attempt to launch it from the roof of a houseboat, it plunged into the Potomac River. The explanation given was that the launching apparatus was defective. This was remedied and a second trial made, but the same result followed. It was never tried again. This machine was really a double or a tandem monoplane. The framework was built of steel tubing almost as thin as writing paper. Every rib and pulley was hollowed out to reduce the weight. The total weight of the engine and machine was 800 pounds, and the supporting surface of the wings was 1,040 square feet. The airplane now in use averages from 2 to 4 pounds weight to the square foot of sustaining surface. About the same time the French electrician Otter, after years of experimenting, with the financial aid of the French government, made some secret trials of his machine which had taken 5 years to build. It had 2 bat-like wings spreading 54 feet and was propelled by 2 screws driven by a 4-cylinder steam engine, which has been described as a marvel of lightness. The inventor claimed that he was able to rise to a height of 60 feet and that he made flights of several hundred yards. The official tests, however, were unsatisfactory, and nothing further was done by either the inventor or the government to continue the experiments. The report was that in every trial the machine had been wrecked. The experiments of Lilienthal had excited an interest in his ideas which his untimely death did not abate. Among others, a young English marine engineer, Percy S. Pilcher, took up the problem of gliding flight, and by the device of using the power exerted by running buoys, with a 5-fold multiplying gear, he secured speed enough to float his glider horizontally in the air for some distance. He then built an engine which he purposed to install as motive power, but before this was done he was killed by a fall from his machine while in the air. Before the death of Lilienthal, his efforts had attracted the attention of Octave Chanute, a distinguished civil engineer of Chicago, who, believing that the real problem of the glider was the maintenance of equilibrium in the air, instituted a series of experiments along that line. Lilienthal had preserved his equilibrium by moving his body about as he hung suspended under the wings of his machine. Chanute proposed to accomplish the same end by moving the wings automatically. His attempts were partially successful. He constructed several types of gliders, one of these with 2 decks exactly in the form of the present biplane. Others had 3 or more decks. Upward of 700 glides were made with Chanute's machines by himself and assistants without a single accident. It is of interest to note that a month before the fatal accident to Lilienthal, Chanute had condemned that form of glider as unsafe. In 1897, A. M. Herring, who had been one of the foremost assistants of Octave Chanute, built a double-deck (biplane) machine and equipped it with a gasoline motor between the planes. The engine failed to produce sufficient power, and an engine operated by compressed air was tried, but without the desired success. In 1898, Lawrence Hargrave of Sydney, New South Wales, came into prominence as the inventor of the cellular or box kite. Following the researches of Chanute, he made a series of experiments upon the path of air currents under various curved surfaces, and constructed some kites which, under certain conditions, would advance against a wind believed to be absolutely horizontal. From these results Hargrave was led to assert that Soaring sails might be used to furnish propulsion, not only for flying machines, but also for ships in the ocean sailing against the wind. The principles involved remain in obscurity. During the years 1900 to 1903, the brothers Wright, of Dayton, Ohio, had been experimenting with gliders among the sand dunes of Kitty Hawk, North Carolina, a small hamlet on the Atlantic coast. They had gone there because the government meteorological department had informed them that at Kitty Hawk the winds blew more steadily than at any other locality in the United States. Toward the end of the summer of 1903, they decided that the time was ripe for the installation of motive power, and on December 17, 1903, they made their first 4 flights under power, the longest being 853 feet in 59 seconds, against a wind blowing nearly 20 miles an hour, and from a starting point on level ground. During 1904, over 100 flights were made, and changes in construction necessary to sail in circles were devised. In 1905, the Wrights kept on secretly with their practice and development of their machine, first one and then the other making the flights until both were equally proficient. In the latter part of September and early part of October 1905 occurred a series of flights which the Wrights allowed to become known to the public. At a meeting of the Aeronautical Society of Great Britain, held in London on December 15, 1905, a letter from Orville Wright to one of the members was read. It was dated November 17, 1905, and an excerpt from it is as follows. During the month of September we gradually improved in our practice, and on the 26th made a flight of a little over 11 miles. On the 30th we increased this to 12 1/5 miles. On October 3rd to 15 1/3 miles. On October 4th to 20 3/4 miles, and on October 5th to 24 1/4 miles. All these flights were made at about 38 miles an hour, the flight on October 5th occupying 30 minutes 3 seconds. Landings were caused by the exhaustion of the supply of fuel in the flights of September 26th and 30th and October 8th, and in those of October 3rd and 4th by the heating of the bearings in the transmission, of which the oil cups had been omitted. But before the flight of October 5th, oil cups had been fitted to all the bearings, and the small gasoline can had been replaced with one that carried enough fuel for an hour's flight. Unfortunately, we neglected to refill the reservoir just before starting, and as a result the flight was limited to 38 minutes. The machine passed through all of these flights without the slightest damage. In each of these flights we returned frequently to the starting point, passing high over the heads of the spectators. These statements were received with incredulity in many parts of Europe, the more so as the Wrights refused to permit an examination of their machine, fearing that the details of construction might become known before their patents were secured. During the summer of 1905, Captain Ferber and Ernest Archdeacon of Paris had made experiments with gliders. One of the Archdeacon machines was towed by an automobile, having a bag of sand to occupy the place of the pilot. It rose satisfactorily in the air, but the tail became disarranged, and it fell and was damaged. It was rebuilt and tried upon the waters of the Seine, being towed by a fast motorboat at a speed of 25 miles an hour. The machine rose about 50 feet into the air and sailed for about 500 feet. Archdeacon gathered a company of young men about him who speedily became imbued with his enthusiasm. Among them were Gabriel Voisin, Louis Blériot, and Léon Delagrange. The two former, working together, built and flew several gliders, and when Santos Dumont made his historic flight of 720 feet with his multiple cell machine on November 13, 1906, the first flight made in Europe, they were spurred to new endeavors. Within a few months Voisin had finished his first biplane, and Delagrange made his initial flight with it, a mere hop of 30 feet, on March 16, 1907. Blériot, however, had his own ideas, and on August 6, 1907, he flew for 470 feet in a monoplane machine of the tandem type. He succeeded in steering his machine on a curved course, a feat which had not previously been accomplished in Europe. In October of the same year, Henri Farman, then a well-known automobile driver, flew the second Voisin biplane in a half circle of 253 feet, a notable achievement at that date. But Santos Dumont had been pushing forward several different types of machines, and in November he flew first a biplane 500 feet, and a few days later a monoplane 400 feet. At this point in our story the past seems to give place to the present. The period of early development was over, and the year 1908 saw the first of those remarkable exploits which are recorded in the chapter near the end of this work, entitled Chronicle of Aviation Achievements. It is interesting to note that the machines then brought out are those of today. Practically, it may be said that there has been no material change from the original types. More powerful engines have been put in them, and the frame strengthened in proportion, but the Voisin, the Bleriot, and the Wright types remain as they were at first. Other and later forms are largely modifications and combinations of their peculiar features. End of chapter 4.